All right, for our lesson today, we're actually going to be combining sections 2.6 and 2.7. We're going to be graphing some rational functions, looking at some behaviors and some features. So let's go ahead and get started. All right, first we want to identify is how to find a vertical asymptote. So for any given function f, if you can plug in a value x, we're going to call that value a, and you get a 0 in your denominator, then you're going to have a vertical asymptote where x equals a. So what that means is, again, we're going to be identifying values that we plug into our denominator to make it 0, which means that at that value, we're going to actually have a vertical asymptote. All right, one of the straightforward ways to find our vertical asymptotes is to simply take our denominator and set it equal to 0. So for your first example, if I set 2x minus 6 equal to 0 and I want to solve for x, I would add 6 and divide by 2 and end up getting that x is equal to 3. And so what that means is 3 is the value that if I plug it into my denominator, I get 0. So x equals 3 is the equation of your vertical asymptote. We can do the same thing with our other example. We have 1 over x squared minus 4. We're going to go ahead and set that equal to 0. And if I were to solve that, I end up getting x is equal to positive 2, and also x is equal to negative 2. Now again, what that means is these are the two values that if I plug them into my denominator, I'd actually get a 0. So those are going to end up representing my two vertical asymptotes. All right, when we're trying to identify horizontal asymptotes, what we're going to be doing is identifying the degree of the polynomials. So for your numerator, generally your first term is going to be your largest term if it's in descending order, and that's going to help us identify our degree. And for your denominator, the same thing, your first term is usually going to be your largest term in terms of your degree. And so once you've identified them, we want to compare them. If, for our first example, if the degree of your numerator is less than the degree of your denominator, you automatically are going to have a horizontal asymptote at y equals 0. Again, if the degree of your numerator is smaller than the degree of your denominator, you automatically have a horizontal asymptote at y equals 0. For our second situation, if instead the degree of your numerator is equal to the degree of your denominator, then what your equation is going to be is whatever your coefficients are, or a ratio of them. And then for our last situation, if instead the degree of your numerator is larger than the degree of your denominator, then you have no horizontal asymptote. Instead, you have a slant asymptote, which we're going to look at later in the section. All right, let's go ahead and apply this. So what we're going to do is identify our largest terms by looking at the degree. For our numerator, there's only one term to look at. We have 2x cubed, and that's going to be of degree 3. For my denominator, 3x is going to be my largest term because it has the highest degree. Now that we've identified them, we're going to compare the exponents. For my numerator, the degree is going to be 3. For my denominator, the degree is going to be 1. So since my numerator has a larger degree than my denominator, this is going to be our scenario 3, and we actually have no horizontal asymptote. For my second example, if I look at my terms, again, we only have one term for our numerator. We have 2x. For my denominator, the largest term is going to be 3x squared because it has the largest degree. When I compare those degrees, I have degree of 1 for my numerator, I have degree of 2 for my denominator, and in this case, my denominator has a larger degree, so this is going to be scenario 1, where the numerator is less than your denominator, and you're automatically going to have a horizontal asymptote of y equals 0. In addition to vertical and horizontal asymptotes, occasionally we might have a hole. So a function could have a hole at x equal to a if both the numerator and the denominator have a factor of x minus a. And this is commonly referred to as a removable discontinuity. So if we have factored our expressions and we see that both numerator and denominator share a common expression, in this case x minus a, we can cancel those out. And so that would actually leave a small gap in your function, which we're going to call a hole, or is also referred to as our removable discontinuity. It would not be a vertical asymptote. All right, let's go ahead and look at how we would identify a hole. So for our initial example, we have x squared minus 16 over x squared minus x minus 12. Now, anytime we want to find a hole, the first step is always to go ahead and factor your expressions. So I've gone ahead and factored my numerator and my denominator. And now what we're trying to identify is, do they have common factors? So I notice in my numerator, I have x minus 4, and in my denominator, I also have x minus 4. So I can go ahead and cross cancel those. And so that tells me I'm going to have a hole when x equals 4. All right, if I go ahead and cancel those out, what I'm left with for my expression is x plus 4 over x plus 3. And now to go ahead and find my hole, I know my x value has to be 4 because that's what I would get if I solve my factor here. I'm going to plug 4 into my remaining rational function. And you can see that I have 4 plus 4 over 4 plus 3, which simplifies to be 8/7. If I go ahead and pair that up with my x value of 4, then I have my coordinate of 4, 8/7, and that is going to be the location of our hole. All right, we're going to go ahead and find our asymptotes here. First thing I want to do a check for, though, just to make sure I can't factor anything to look for holes. I have 4x and then 2x plus 8. Nothing's going to factor to cancel there. And then 4x squared and x squared is minus 9. Again, nothing will factor there. So now I can go ahead and look for my asymptotes. I'm going to start with finding my vertical asymptotes. For my first function, we're going to take our denominator, 2x plus 8, and set that equal to 0. And if I solve that, I end up getting x is equal to negative 4, which is my vertical asymptote for that equation. For my second one, we'll do the same thing. I'm going to take my denominator, x squared minus 9, set that equal to 0. And when I solve that, we're going to add 9 and take the square root. So we actually got to remember to put in our plus or minus here. But we get x equals plus or minus 3 for our vertical asymptotes there. All right, we're going to go ahead and find our horizontal asymptotes now. To do that, we're going to look at our largest terms in numerators and denominators. In my first equation, the largest term in the numerator is going to be 4x. My denominator is going to be 2x. I want to look at the degrees there. Notice that I have a degree of 1 and another degree of 1, which means my asymptote is going to be a ratio of those two terms. To find that, we're going to go ahead and write that out. Y equals 4x over 2x. And when we simplify that, we get y is equal to 2 as our horizontal asymptote. We're going to do the same process for our other equation. Again, identifying our largest terms in numerator and denominator. I have a 4x and an x squared as my largest terms. Again, look at the degrees. We see the degrees are once again the same. So for my asymptote, it'll be a ratio of those two values. We'll go ahead and set that up. Y is going to equal 4x squared over regular x squared. And then when I solve that, we get y is equal to 4 as our asymptote. So there you have it, our asymptotes for those two functions. When we're trying to find our intercepts, there's two to talk about. We have the x and the y intercepts. If I am looking at my x-intercepts, what I'm going to be doing is I'm going to set the numerator equal to 0, and I'll solve for x. And that will give me the value for my x-intercepts. If I instead want to try and find my y-intercept, what I'm going to end up doing is I'm simply going to plug in 0 for my x value, and the number I get is going to represent our y-intercept. Let's go ahead and apply this. All right, we're going to go ahead and find both of our intercepts. For our x-intercepts, we're going to go ahead and take our function and take the numerator and set it equal to 0. So if we do that, we end up getting x squared minus x equals 0. I'm going to factor this, giving me x times x minus 1. And then if I set each factor equal to 0 and solve, we have x equals 0, and then we also have x minus 1 equals 0, which means that I have two intercepts. I have one at x equaling 0 and one at x equaling 1. And if I write those as points, we have 0, 0, and then we have 1, 0. All right, for my y-intercept, we're going to plug in 0 into our x values. So I'm going to plug in a 0 into my three x values and simplify. So I end up getting 0 squared minus 0 over 0 plus 1. That whole thing simplifies to be 0 over 1, which is just 0, which means that my y-intercept is also going to be 0, 0. And now I have my x and my y-intercepts. We're going to go ahead and apply this one more time. Again, to find our x-intercepts, I'm going to start with my numerator, and I'm going to set that equal to 0. So we have x squared minus x minus 2 equals 0. If I factor this, then we get x minus 2 and x plus 1. And again, we have to factor this to get each factor equal to 0. So then we have x minus 2 equals 0 and x plus 1 equals 0. When I solve each one of those, we get x equals 2 and then x equals negative 1, which means we have two x-intercepts. One of them is at 2, 0. One of them is at negative 1, 0. For our y-intercept, we're again going to go ahead and plug in a 0 into our x value. So we have, again, three x values to plug in a 0. And we'll simplify what we have when we're done, which means we have 0 squared minus 0 minus 2 over 0 minus 1, which will simplify to be negative 2 over negative 1, which is equal to 2. And that tells me I have a y-intercept at the point 0, 2. All right, we're going to go ahead and put it all together now. We're going to try and find all of our information to graph this function. So to begin with, I'm going to go ahead and set my denominator equal to 0. So I get 3x plus 6 equals 0. And when I solve this, I end up getting x is equal to -2, and that's going to be my vertical asymptote. So I'm going to go ahead and draw that in. We got a vertical asymptote going around x equals -2. For my horizontal asymptote, I'm going to look at my terms in my numerator and my denominator and compare them. The biggest term in my numerator is 2x. In my denominator, it's 3x. When we look at the degrees, they both have degree of 1. And since the degrees are the same to find a horizontal asymptote, we're going to set a ratio. So we have y equals 2x over 3x, which means y is going to equal 2/3 for our horizontal asymptote. I'm going to go ahead and draw that here. It's close to 1. It's kind of hard to sketch this with my graph, but it's about there. Okay, now we want to go ahead and find some intercepts. To find my x-intercept, I'm going to take my numerator and set it equal to 0. And when I solve this, I get 0, so I have the point 0 and 0. So I'm going to put a point right there for 0, 0. When I do the same thing for my y-intercept, when I plug in a 0 to find my y-intercept, we again get these same points. So in this case, the x-intercept and the y-intercept are in fact the same. Okay, we need a couple more points here. So what I'm going to do is I'm going to kind of set up a little t-table here. And for my t-table, I'm just going to pick a value on either side of my vertical asymptote. So since my vertical asymptote is at -2, I'm going to say -3 and -1 to help me get an idea of where my graph exists. All right, so when I plug those into my function, I end up getting a 2 when I plug in a -3, and I get a -2/3 if I plug in a -1. So I'm going to go ahead and graph those as well. So at -3, I have a 2, and then at -1, -2/3. So right around here. And what I'm basically trying to see is where is my graph in terms of my asymptotes. And I know I have to follow along them. And I can see that I have something down here on the bottom right portion, and then something up here on the top left. So what I can do now is I can trace a graph that's going to go through those points and follow along my asymptotes. So I have something basically like this, and then I have this as well. And now we have the graph of our function with the correct asymptotes and intercepts. All right, next example here, we're going to go ahead and do everything. We're going to find the asymptotes, we're going to find the intercepts, and we're going to go ahead and sketch it. First thing we definitely want to do is go ahead and try and factor this. So for my numerator, I can factor it as 3x minus 2 times x minus 2. For my denominator, we can factor this as 2x plus 1 and x minus 2. And notice that they share a common factor. They both have an x minus 2. And what that's going to do is we're going to simplify that, or cross cancel, and it's going to end up representing a whole in our function. So for everything else, I'm going to go ahead and just evaluate it using my remaining expressions, 3x minus 2 and 2x plus 1. Okay, so let's go ahead and try and find our vertical asymptote. For that one, we're looking specifically at our denominator. So I'm going to say 2x plus 1 is equal to 0. When I solve that, I get x is equal to -1/2. I'm going to go ahead and try and sketch that. Again, it's a little hard with my graph, but we can kind of see it's between 0 and -1. For my horizontal asymptote, I want to look at my biggest terms. So I have a 3x and a 2x. They both have degree 1, which means I'm going to write it as a ratio, 3x over 2x. And if I simplify that, we get 3 over 2. Okay, I'm going to go ahead and graph that as well. So that's about 1.5, right? Something about here. Now I'm going to try and find my intercepts. So to find my x-intercept, we're going to go ahead and take our numerator and set that equal to 0. So we have 3x minus 2 equals 0. If I solve this, I end up getting x is equal to a positive 2/3. So at 2/3, 0, I'm going to have my x-intercept. For my y-intercept, I'm going to plug in a 0 and simplify that. And if I do, we get 0 minus 2 over 0 plus 1. And that's going to simplify to be -2. So I know then at -2, 0, I have another intercept. Just like with our last example, we want to try and set up a t-table here because I need to find points on both sides. I already have some points on the right side of my vertical asymptote, so I'm going to find some points on the left side. I'm going to plug in -1 and -2. So if I plug in a -1, then I end up getting a 5. And if I plug in a -2, then I get 2 2/3. I'm going to go ahead and graph those points. So I have -1, positive 5, and then -2, 2 and 2/3. So we can see again for our graph, on the right side of our vertical asymptote, we're going to have this feature. On the left side, we're going to have this feature here. So I'm going to go ahead and connect those dots. And we now have our rational function. All right, if we don't have a horizontal asymptote, then that means that we're going to be having what is called a slant asymptote instead. And that's going to happen if the degree of the numerator is greater than the degree of the denominator. And the way we're going to be finding this is we're going to actually be doing some division. We're going to divide the numerator into the denominator, and what we're left with is going to be our slant asymptote. Now, to do this division, we're actually going to be doing long division. So let's go ahead and do an example. We're going to go ahead and try and find our slant asymptote, and we just want to verify that we do have one. So in our numerator, notice the degree is going to be squared, or 2, and our denominator degree is 1, and since our numerator has a larger degree, we do not have a horizontal asymptote, instead we have a slant asymptote. To find that slant asymptote, we're going to set up long division. So we have x plus 1, and we're going to divide that into x squared minus x, and I'll put plus 0 so we have a constant term as well. The first step is we want our first term in each expression to end up being the same. So I have to multiply my x by an x to turn it into an x squared. Go ahead and put that up here. And then I'm going to multiply, so x times x is x squared, x times 1 is positive x. We're going to go ahead and subtract those. And my x squares cancel. When I do negative x minus an x, I get a negative 2x. Bring down to 0. And now we repeat our process. I now need this x to be the same as this negative 2x. In order to make that happen, I'm going to go ahead and multiply by a negative 2. So that gets me negative 2x minus 2. And then when I subtract those, my x's will cancel, and I'm getting a positive 2, which is my remainder. Now, I'm not super concerned about the remainder. For my slant asymptote, it's going to just be what I have outside of that. So this x minus 2 is going to represent the equation for my slant asymptote. So all I need to do is put a y equals in front of it, and now I have the equation of my slant asymptote. All right, we're going to go ahead and find all the information for our rational function here. To begin with, we're going to investigate if we have a whole or not. For my numerator, I have x cubed, which I can't really factor. For my denominator, I can factor that as x minus 1 and x plus 1. And notice that we don't have anything to cancel, so we do not have a whole. I'm going to go ahead and move on to find my vertical asymptotes. To do that, I'm going to take my denominator again and set that equal to 0. So we have x squared minus 1 equals 0. And if I solve that, we end up getting x is equal to plus or minus 1. So that's going to be the equation for our vertical asymptotes. For our horizontal asymptote, I want to look at my terms here. So if I compare x cubed to x squared, notice that my numerator has a bigger degree than my denominator, which means I do not have any horizontal asymptotes. So instead, I'm going to move on to finding my slant asymptote. Again, to do that, what we're going to do is set up long division. So I have x squared minus 1. That's going to be going into x cubed. And I'm just going to fill out my terms here. 0x squared, 0x, and then plus 0. Okay, I want to line up my terms, so I need x squared to be the same as x cubed. To make that happen, I'm going to multiply by an x. And if I do that, I end up getting x cubed minus x. If I subtract, I end up getting just a positive x. And this positive x is actually a remainder because there's no way I can take x squared and divide it into that x because my degree is already too big, which means that for my slant asymptote, I have the simple equation of y equals x. Okay, I found my asymptotes. I found that I do not have any holes, so now I want to find my intercepts. To find my x-intercept, I'm going to take my numerator and set it equal to 0. So I have x cubed equals 0, and I get just x is equal to 0, which means that I have the point 0, 0 as my x-intercept. From my y-intercepts, I'm going to plug in 0 into my equation, and plug in 0 for my x values. That gives us 0 over 0 minus 1, which is, again, going to just be 0. So we have these same x and y-intercepts. Okay, we're going to go ahead and graph all this stuff on the next slide and then try and trace out our function. Okay, so just to review, we have vertical asymptotes at plus or minus 1. We have a slant asymptote at y is equal to x, and then we have an intercept of 0, 0. So I'm going to go ahead and draw in my asymptotes. Here we have positive 1, and here we have negative 1. And then for the slant asymptote y equals x, it's a diagonal that cuts our grid. And last but not least, I have my intercept of 0, 0. Okay, we have a lot of information that we need to kind of find. We need to figure out what's happening on both sides of our vertical asymptotes. So I need to figure out on the left of negative 1, on the right of negative 1, on the left of positive 1, and on the right of positive 1. So I'm going to go ahead and set up a t-table real quick. And I'm going to go ahead and do -2, -1/2. That'll take care of my left vertical asymptote. And then +1/2 and +2, and that's going to take care of my right vertical asymptote. All right, so what we end up getting for our values, we get -2 2/3, +0.167, -0.167, and then +2 2/3. So I'm going to go ahead and graph those points on my graph here. I'm going to talk about what the shape looks like. Okay, so -2 2/3 is going to be below, so it's going to be right around here, below our slant asymptote. Then we have 0.167, which is right around here, -0.167, which is right around here, and then +2.67, which is above our slant asymptote. Okay, so for our behaviors, again, we can't cross over asymptotes, which means down this corner, we're going to be following on the asymptote and then coming down the vertical. On the top right corner, the same thing. We're going to be following along our asymptotes. The weird part is in this middle here, notice that we have one of our points which is actually on our slant asymptote. Now, one of the unique things about intercepts is that is the only location where a graph can actually cross through an asymptote. So for our shape, if we connect all of our dots, we have this kind of shape on the bottom left, on the top right, again, following through asymptotes. But in the middle here, because we have that intercept on an asymptote, it snakes through. All right, guys, that does it for our notes. Go ahead and get started on the homework. And this is, again, the video for 2.6 and 2.7. So good luck with that.